In this video, we're going to look at the second part of section 1.6, which is on rational functions. Rational functions are functions where you have a function in the numerator and a function in the denominator, so they're fractions. Now, when we have these polynomials, we assume that there are no common factors in the numerator and denominator, and that the denominator does not equal 0. Let's look at some. Here we have 4 examples. My first example is of the graph of f of x equals 1 over x. My second is 1 over x squared. My third is h of x equals x minus 3 over x squared plus x minus 2. So this one is a little more complicated, but you'll notice that the equation itself is a little more complicated also. And in my fourth example here, j of x is 2x plus 5 over 2x minus 6, and it has a graph that looks like this. Example 1 tells us to determine the domains of these graphs by finding the vertical asymptotes that restrict the domain. So a vertical asymptote is a line that is not part of the function, but that the curves approach and get very close to, but never touch. And the way we find them is by setting the denominator equals 0. So with f of x here, in my first graph, f of x equals 1 over x, we would say x cannot equal 0. That means that's my vertical asymptote. My vertical asymptote is x equals 0 because it can't equal 0. Let me explain. If I substituted 0 in for x, you would have an undefined function. So x cannot equal 0. That's why this curve approaches it but never touches it. And the equation of this vertical line is x equals 0. So that's my vertical asymptote right there. In my second equation, similarly, we'd say x squared cannot equal 0. If you take the square roots of both sides of there, you would find that for g of x, my vertical asymptote is x equals 0 once again. Why? Because x cannot equal 0. In my third function, we look at our denominator, which is x squared plus x minus 2. And we say x squared plus x minus 2 cannot equal 0. When we find where it does equal 0, that is our vertical asymptote. Factoring this, we're going to get x plus 2 times x minus 1. Because if you multiply these two together, you get a negative 2. If you add a positive 2 and negative 1, you get a positive 1. So it factors to x plus 2 times x minus 1 equals 0. So what this means here is that x plus 2 equals 0 would make this equation equal 0. Or x minus 1 equals 0 would make that equation equal 0. If we add or subtract 2 from both sides here, we're going to get x equals negative 2. And if we add 1 to both sides, we'll get x equals 1. So those are our vertical asymptotes for the function h of x. X equals negative 2 and x equals 1. So if I did substitute a 1 into this function, for example, in my numerator, I'd have 1 minus 3, negative 2. And if I substituted 1 into the denominator, I'd have 1 plus 1 minus 2, which is 0. That can't happen. So x equals 1 is a vertical asymptote. So we can draw this in here. That's the line x equals 1. And the line x equals negative 2 would be a vertical line that crosses the x-axis at negative 2. Let's look at j. In my j of x function, we'd look at our denominator and say that 2x minus 6 cannot equal 0. Solving this, we'd add 6 to both sides and then divide by 2 and get x cannot equal 3. Therefore, x equals 3 is the vertical asymptote. You drew that, x equals 3. That's what you get. So to determine a vertical asymptote, where P of X and Q of X are polynomials with no common factors other than constants, and A is a zero of the denominator. The line X equals A is a vertical asymptote for the graph of the functions. That was, again, if our function R of X is P of X over Q of X. So let's look at example 2 and find the vertical asymptotes for the graphs of each of the functions. What we'll need to do is, I like to factor the numerator and denominator if they factor, just in case. In my numerator, 2x minus 11 doesn't factor because they have no common factors. But in the denominator, we'll be factoring that. So we think what two numbers will multiply together to give us a -8 and add together to give us a +2. And that would, of course, be x plus 4 times x minus 2. If you multiply them, you get a -8. If you add them, you get a +2. So then we set those denominator values equal to 0, those factors. And that would lead us to determine that x equals -4 is a vertical asymptote. And here, by solving this by adding 2, we get x equals 2 as a vertical asymptote. All right, let's try it in B. In B, if we factor our numerator, we'll have, well, let's factor both. You can factor an x out of both terms in my numerator. So we'd have h of x would be x times x minus 4. In my denominator, I can factor an x out also. And we'd have x times x squared minus 1. So, so here we have a factor in common. The x can cancel in each place. And so x equals 0 is not going to be a vertical asymptote. It'll just be a hole in the graph. When you have cancelable factors, will be a hole in the graph, and we'll look at that. Now we look at these. Can we factor these any further? X minus 4 cannot be factored further, but x squared minus 1 is the difference of squares. So it will become x plus 1, x minus 1. So this h of x simplifies to this, x plus 1. That means that x plus 1 equals 0. That'll determine one of our asymptotes. And x minus 1 equals 0 will determine our other asymptote. So we subtract 1 and get x equals -1. That is a vertical asymptote. Here we'd add 1 and get x equals 1. So both of those would be vertical asymptotes of this function. Looking at G, we have x minus 2 over x cubed minus 5x. So our numerator does not factor any further, but in our denominator, we can factor an x out of both of those terms. And get x times x squared minus 5. Now this one is also, you could do it as the difference of squares, and that's actually what I'm going to do. So my denominator here has x, and this can factor to x plus the square root of 5 times x minus the square root of 5. So we have 3 potential vertical asymptotes here. This x does not cancel with the x in the numerator, because in order for a variable to cancel in the numerator or denominator, it has to be multiplied by something else. So that's why these x's canceled in B. But here, this x in the numerator is not being multiplied, so it won't cancel. Here, we'll find then that our vertical asymptotes are x equals 0. This one, we'd subtract the square root of 5 and get x equals a negative square root of 5. And here we'd add the square root of 5 to get x equals the square root of 5. So those are our 3 vertical asymptotes for our third equation here. Okay, so in our next video, we are going to look at how to graph a rational function. Thanks for watching.